Perhaps you've encountered this fella, or more commonly, the diagram illustrating his exclusion principle. Meet Wolfgang Pauli and his spin matrices. These are crucial tools for grasping the quantum essence of spin, particularly for spin 1/2 particles. Pauli's pioneering work on spin continues to intrigue, and today we'll witness these matrices in action. How are we going to do that? Well, let's consider an electron in the spin state of chi equal A, 3I, and 4. For part A, we're going to determine the normalization constant A. B, find the expectation values of the spin in the x, y, and z directions. C, find the quote uncertainties, which are really just the standard deviations, in the spins of x, y, and z. And D, confirm your results are consistent with all three uncertainty principles. So, stop number 1 on this journey. We are going to have to normalize. In the same way that we did in the first chapter of the book, getting used to normalization with integrals, now that we're dealing with certain states and we have the Dirac notation, this is going to be vectors, so we have to use the inner product. Same kind of concept, just with a slightly new face. So instead of psi star psi, we end up with a dagger, which stands for conjugate transpose. This, again, we need for the dimensionality. If you want the more kind of nitpickiness of it, check out the PDF that is below. But nonetheless, let's continue. We see if we plug in the state that we were given with A and 3I and 4, we simply need to apply the conjugate transpose, which is the dagger. So we switch the dimensionality of this column vector into a row vector. And then if you have a matrix, switch everything accordingly. This turns into the A star that we saw with the wave functions, but now it's an A dagger. A-OK, bring it all outside, constants are good there. Now we're in the right place for matrix multiplication. Again, a vector is a particular type of matrix, so don't be scared if you see that those words get interchanged. You're A-OK. So take the magnitude squared of A and then multiply across row to column. And you see that we get 3i and 3i. This is where the conjugate transpose comes in to make sure we have a positive there. So the negative, negative 1 coming from the I squared goes to a positive 9, and then you have a positive 16. So we end up with A squared times 25. Since we want this normalized, it's equal to 1. So divide over the 25, take the square root to get the magnitude of A. So we see that A is equal to 1/5. Put that back together in the spin state, and now you have your normalized spin state. Moving forward on to stop number 2 then, since we have it normalized, we can now go ahead and find the expectation value. I do warn you, sometimes this step is also complete with the first step, and when we see here that we have the expectation of S of x, what we really have to understand is that with this being in Dirac notation, this used to be an integral, and now we have this with the bracket stuff in between, to where we have this acting on this state here. Again, same concept, just be aware that the notation does change because we're dealing with states now, not functions. That being said, same concept. If it's not normalized, what we do is divide this expression by chi and chi, the inner product of chi and chi. So I have that in the PDF just to be aware. Some authors just put that straight into the definition. Same thing if you were trying to find a weighting function in calculus, something to that effect. All right, so now that that ramble's out the way, let's go ahead and chug along. We see here that this looks like chi dagger Sx chi, but what is Sx? Well, if we recall from the text, S was equal to the spin matrix, which was h bar over 2 times sigma x. Sigma here stands for the Pauli matrix in the x direction. This is a very special class of matrices that we'll touch on in just a second, but what we need to realize is that S is related to these Pauli matrices. So with, of course, a factor of h bar over 2. So when we plug everything in, we have a very similar setup. Okay, so here we have h bar over 2 and A dagger A, which is A squared, which we saw last slide. So now what we need to do is multiply this matrix into this column vector and find a new column vector. So row to column, and we're good. And we see that when we do that, we get 4 and 3i. That being said, if we multiply this row vector into this column vector, we get a negative 12i plus 12i, so they cancel out completely. That being said, we still have this h bar over 2 that just comes down, and we saw magnitude a squared was equal to 1 over 25. You're good to go there. The 0, of course, should tell us something about the kind of symmetry we're dealing with regards to the spin in the x direction. So keep in mind, this is telling us a much bigger picture that we might not see just yet, just from the sheer computation. But let's continue with the other two. So, of course, we have to do the same thing for the y and the z. We'll follow suit, so I'm just going to kind of speed line this through. Here is the Pauli matrix for the y direction. Again, in the PDF, this is all kind of, repeat effect, so if you want to see more of the detail, check that out. But here, you see that the construction of this Pauli matrix looks similar, but slightly different since we have the i's here. So just be aware your matrix multiplication is going to look a little clunky because i's tend to clutter everything. That being said, run it through. You see we get negative 12 and negative 12 all real, even though we had i's here. So there you go. Cancel, cancel, because you have two factors here. So the factor of 2 from this and the factor of 2 from h bar over 2 cancel away, and we're left with a negative 12 over 25 h bar. Easy enough to deal with. Similarly, moving down to z, we see that we have yet another weird looking matrix with 1, 0, 0, negative 1. Again, all of these are very special, which we'll touch on in just a second, but when we multiply them through, we get another negative. Kind of weird to have a negative expectation value, but again, I think what is going to be apparent very shortly is how all these things tend to come together. That being said, let's move on and, well, at least catch up to the part of the question that we're in. We normalized it, and now we found the expectation value for all components. Let's go ahead and move on to our third stop. All right, so moving straight along then, we now need to find the quote uncertainties. Again, this goes back to the statistical definition. This is the standard deviation from the variance. Here, again, we can compact this form by using some index. Use whatever variable you want. Just be aware I might be clunky since we're dealing in complex natures or complex numbers as well. That being said, J is indexed through 1, 2, 3, and those represent x, y, and z in this case. That being said, if we want to square, we need to have this as the chi-dagger matrix setup squared, so h bar over 2 sigma x squared. And that means that we apply the matrix twice. Okay? And in doing so, it's best to handle these two matrices together first. That's kind of a bit of hindsight that's telling us why, which we'll see in the next showing. But understand, if you multiply this into this first, and then this again, you're going to see something that they kind of undo one another. That's because of the properties of the Pauli matrices. So if we just handle blue, we see that we get multiplication with these two things. We get back this should look familiar matrix. That being said, this multiplied to this gives us back this column vector because this is the identity matrix. So that being said, we end up with the pretty similar setup to what we had when we first tried to normalize it. And that's exactly what we get. That's why we end up with 25 here in the brackets, which cancels out with our normalization factor, leaving us with just h bar squared over 4. So this begs the question, this seems familiar and easy, maybe too easy. I wonder why. Maybe there's a shortcut. Let's see what that shortcut is. Of course, this leads us directly to the fact that we can use the construction of the Pauli matrices and their properties. Just by a look of the sigma matrices, the spin matrices, we see that for x, y, and z, if we take them out, of course, this is just showing the math so you can see how, even with the i's, everything works very nice. They all come back to the identity matrix. This is truly fascinating and has a whole host of properties that are very important for what is to come in the rest of physics. Particularly, if you like the group theory, this is an example of the SU2 groups, which are isomorphic to the SO3 groups. All of these are dealing with symmetries and have particular properties within each group structure. So if you want to learn more about that, these are very good things to have in mind as you move to the other parts of physics especially particle physics and quantum field theory, where you're looking at these continuous groups with the Lie groups and things of that nature and how they transform with one another. The SU2 stands for special unitary matrices of order 2, or 2 by 2, so to speak. So there's a lot of properties there that are very special to what we have further in the development of the theory, all stemming from what we witness here with these matrices. Very, very important and very, very fascinating to dive into. What you'll also notice about these matrices is they have some weird properties. Their determinants are -1 and they are traceless. Traceless meaning that the sum of the diagonals is 0. 0 and 0, and the determinants all equal -1. So very weird setup. All that to say is that these things are both they are their own inverse, and that's a whole special class of matrix. They are their own Hermitian conjugates. So very, very important. I can't emphasize enough how important and fascinating these are. So without losing the scope of this question, be aware that is a great thing to look into if you're curious, and I'll probably do a video on that at some later point. It's always been a curiosity, and that's what we're here for. So let's go ahead and finalize how we can pull all this together for this example. That being said, because all of these equal the square equals their identity matrix, we know that for all square expectation values, we end up with h bar squared over 4, regardless of x, y, or z. That's very useful and very helpful. So anytime we're trying to find the uncertainty or the standard deviation, this is what we end up with in all our calculations. This first value is h bar squared over 4, and we can just simply plug in the first expectation value that we found, and we see that we get one of the limits of h bar over 2. Let's go ahead and see what the other two look like. Here, of course, since our expectation for y and z weren't so nice, we have to do a little bit of work. Not too bad, though. Here you see we get a couple of squares, 144 over 625. Then, of course, when you find a common denominator and minus them, you get a couple more squares, 79 over 2,500. So after we factor out the h bar squared, which goes to h bar outside the square root, we get a nice simplification. It works out really well, regardless of the fact that these expectations were negative. That being said, if we go ahead and plow through on the z, we see that we get a 12 h bar over 25. Here's an interesting fact that I found in this question, and that you might see as well in other style questions. And in the PDF, I made a table of it so you can kind of see it. Note that the expectation for SY is equal to -12 over 25, but the standard deviation in SZ is 12 over 25. Weird, huh? But also that the expectation for SZ is 7 over 50 with h bar, but the standard deviation in SY is 7 over 50 h bar. Little weird, isn't it? Or maybe it's not if you can see the writing on the wall. That being said, we now reached our third checkpoint, or second checkpoint really, because the expectation and the standard deviations kind of blend together. But part C is now complete, and we can bring it on home to part D. Wonderful. So now that we're at our final resting point for stop number 4, we know that the cyclic permutations, which we learned about in the angular momentum, which in that case was the orbital angular momentum, the extrinsic, here's the intrinsic spin, or intrinsic angular momentum as defined by Griffiths. We see that we know if we go from x, y, z, and then we cycle that x to the end of the line, so we have x, y, z, push this over here, we get the next relation. So we get s, so then we have y, z, x. If we take this y, push it up to the end, we get z, x, y. That's what it means to be cyclic permutations. We're just running in a line, putting them in a circle. So if we plug everything in by the color coordinations, we see here that we have 3 separate uncertainty relations. Again, this was more from the generalized uncertainty principle, so that should be ringing a bell to you. We plug them all in, and we see that indeed, we get here x and y is at the limit, so that's good. We see here that this is well above the limit because it's the limit is at 0 due to the sx equals 0. That's pretty cool. And of course we have z and x at the limit as well. There's a lot more that can be said about this, but for this question, I think that's enough. But it does ring some interesting tales on what is to come and why these are so curious in the scope of quantum field theory and their groups. So be aware, lots more to come from just this concept alone. So much has been studied about spin, it is enormous. All right. So, as always, thank you for watching. Outside of my ramblings and getting back to it from having travel, this was a lot of fun to deal with in this particular question because there is so many ways to talk about spin and so many properties that we just can't fit in one video. But what we were able to cover was how to normalize with a particular spin state, finding their expectations, understanding their quote uncertainties or their standard deviations, and then finding the uncertainty relations via the cyclic permutations. I cannot stress enough how important these matrices are and how vital they will be to the development of much of the other theories, especially when you look into what their eigenvalues are and their eigenvectors, because they're going to look so familiar to you that this will help explain the Pauli exclusion principle as well. And that's probably something that we know of firsthand from chemistry and several other things because of spin one-half particles like electrons. Lots more to come from this, and it's going to be a fun ride, so let's enjoy this journey. See you at the next one.